Okay, I'm going to work through whiteboard problem 26.1. And so it tells us that we have a function for the electric potential. So we're given that the potential V equals 100x squared, and it's telling us that's in volts, right, which is what potential should be. And so I just want to mention right off the bat that we're doing a little voodoo with the units here, right, because when we plug in x, we don't want to put a unit on it because it already has this expression already has a unit of volts, so we wouldn't want to put meters in there again. Okay, and then we need to find our electric field, Ex, at x equals 1 meter, and then also x equals 2 meters. Okay, so if we are given potential and we need to find electric field, we have to remember the relationship between them, right? So that our electric field in a particular direction is negative our change in voltage over change in position. So that's how to think about it in terms of non-calculus. If we wanted to do that for a function like this, where we want to actually create a function for electric field, then we would do so for example, the electric field in the x direction is negative dV dx. And this one is only in the x direction, so we just need to worry about the derivative in the x direction. Okay, so we need to take the derivative of this potential function, right? So Ex is negative d dx, and then our function for potential was 100x squared, and we'll hang on to that volt unit. Okay, so 100 is a constant that just pops out of the integration, and so we just need to know what the derivative with respect to x is of x squared. And so when you have x to a power, you bring the power down in front to x, and then you reduce the power that you started with by 1. So 2 minus 1 is 1. And x to the 1 is just x. Okay, so if we do our derivative now, so we have negative, we're going to bring our 100 outside, d dx of x squared, right? And that's in, we'll talk about the units in a sec. And so that's going to give us a 2x in here. And so then our potential is negative 200x. And now if we look at it, it's a little easier to see when you think about electric field as a change, discrete change in potential over change in position. So if we take our units of volts that we started with, we're dividing by a distance, right? So we're taking our volt and then dividing by a meter. And so that gives us the potential at a particular location x. Okay, so now we can answer the question. So now we can plug in, right, at x equals 1, our electric field is negative 200. Again, we're not going to put a unit on here. We're just going to say that's 1 because we already have our units of volts per meter worked out. And so that's minus 200 volts per meter. Ex. Okay, and then we can do that quickly at x equals 2 as well. We're going to plug in Ex equals negative 200, and now x is 2, and we're still using volts per meter, and so we get negative 400 volts per meter. And that is that.